to tell you guys a secret. I'm watching me. How's it going, guys? Alright, so you probably noticed if you watch my channel, in the videos that I've been uploading, you may have noticed a video where I was teaching a class and I noticed that I was really overweight. I was like, wow, that's pretty bad. So I got out of the Army in 2012, and I think it took about a semester, and I had some financial issues at the time. It's a long story, but when I was in the Army, I actually had saved up $20,000, but I couldn't spend that money right off the bat because I was dumb enough to buy silver. And then I was a student, and suddenly when you get out of the Army, you don't have to do your running and things like that anymore, and you also don't have all this choice of food that can potentially be healthy. And yeah, I literally remember not having much money at all, and I was just like, I'm hungry, and I just want to snack and play Minecraft or whatever for now. Now, I did my homework. I was a good student. But this is annoying. It's like I'm trying to orient my head so that you can see the lambda plus plus thing. Where is it? I can't do this. But yeah, it's like, ugh, chocolate ice cream. Not good. Since then, I've had a lot of jobs in my college town. I did a couple little jobs here and there during the summers. But yeah, in 2012, when I went back to my classes, it seemed like I understood everything more than all the other students in the class, because I would raise my hand and be like, oh yeah, you use this data structure. Like, I knew how to do the C++ class because it was so similar. I already knew Java and already knew data structures because I had already taken basically a year of computer related stuff. The first semester, about 4 years before that, before I joined the Army, I'd went to University of Illinois in Chicago, and I had gotten a 4.0 GPA my first semester studying computer engineering. And so I think one of my classes had to do something with MATLAB, and I knew what I was doing basically in those classes. They were pretty easy. Now, I was taking the train to Chicago every day, so I couldn't sustain this thing, and a lot of things were on my mind. I had this girlfriend from high school that I thought I was supposed to be with on my mind. I had things that I was learning about our society and stuff on my mind. I had things and then taking the train every day and getting tired of that. So my second semester, my grade really dropped. And I think I switched my major too, so I was computer science. And then I was playing a little bit of StarCraft. I think the first time I stayed like overnight or late in Chicago, my mom got scared because she knew I was coming home every day on the train. She's like, why did Tim just not come home on the train? And I don't know. I guess I didn't tell her or something. I don't remember. But that semester was my second semester, and I had gotten a 2.0. So then they averaged out. They're like, make sure you get a 3.0. So they literally averaged out to precisely 3.0. It was hilarious. And I was like, yeah, this is not good at all. My dad basically helped me out with that first year of tuition, and then after that, he was using money. He was like desperately trying to get money, I guess, from some company, and he probably shouldn't have even gave me that money, because he wasn't even able to help out my other sisters with college. So I should have found some way to like work while I was going through school or something. But I figured, you know what, maybe I'll just join the military and use the GI Bill or something to pay for it, and maybe join for a year and a half. Well, I ended up switching and staying in for 4 years and doing Patriot missile system stuff. So luckily, I was really lucky. It's a long story how this happened, but I was lucky enough to be able to go to Japan when not everyone would go there on their first station. And then I was also lucky enough to not have to go to a second duty station due to how much time I had left, probably due to the fact that I had switched. So I ended up never actually being stationed anywhere in the States. I was in Japan after all my training was done in Texas. So yeah, that was really interesting. That was an interesting season. I was in Okinawa for 3 years. Think about that. Okinawa. I was there for 3 years. That's the PFC. There's a guy named PFC Shipman. He was a kid, probably younger than me at the time, who died in a car accident. And he loved really fast cars, and I think he had like a nice car there. I don't know what trade or how he got it, how, saved up money or something like that. But they made the T-shirt in honor of him. But yeah, it was an interesting place to be. I mean, and it was nice, and the people were nice. I mean, they weren't easy to connect with, but at the same time, they didn't like try to, hurt you. You could you could trust the people outside of the base, which we had this, barbed wire fencing. You could trust them more than you could trust the people on the base to not, steal your stuff. So it was an interesting setup there. U.S. military on a very peaceful island, if you ask me. Now, there's wars on the island, but that's not the island people. That's U.S. and China and Vietnam and whoever, Japan, all trying to take over things in World War II and things like that. It's not, the island itself. In fact, they don't even really, I don't think, like Japan saying that they own the island, the actual native people to the island. They kind of consider themselves their own native people. Now, where am I going with all this? I don't know. I'm just talking. Because I had to, I figured I'd upload a video. Again, because I upload one every day. And I don't know if that's a good idea, because I've been uploading one every day. But it was to make sure that my channel was making some sort of progress. Now, if I just have to put some filler and I'm trying to work, 2 jobs and then make a video on top of that, and I'm really tired, I can't really do much except talk about a couple things here and there. There's some things that I could still talk about, like this one time when I was working at Runtime, I posted a Stack Overflow question, and everyone jumped on it and thought it was like a bad question. It didn't make sense. And I still, to this day, I'm like, this question made sense. It was more, in my opinion, like a math question, even though it was a question about the C programming language. But really, we had our own C semantics, which is a mathematical construction of the C programming language. And people said, well, C has bugs by nature, and somebody thought I was trying to be famous. And that's not true, because my boss told me to ask the same question that I asked on there. So, and he kind of put that at the end, like after they blocked me from like doing anything more on the question. He basically said, you're just trying to get famous. Because I said, what C programs, if you find a bug in them, would make you famous, basically. But that's what my boss told me to ask. He said, find, some C programs that would make us famous if we found bugs in it, because that's precisely what they were trying to do. That's not, no joke, what they were trying to do. They literally, we were constructing a mathematical expression which contained the entire Linux operating system. When I was just doing my random tests on things, I was like, okay, let's try to compile, Linux with this. And that's what it does. It converts everything to one mathematical expression. And so all these statistical laws that these guys were talking about, that's like, well, if there's a bug, somebody is bound to find it due to blah 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 statistical law. That's not a theorem. That might be a statistical theory, like a statistical statement, but that's not a proven fact that no matter 100% for sure that people are going to find bugs and things. That might be something observed statistically, but that doesn't mean that it's always true. It's like dropping a bowling ball. Is it a law or is it a theorem? Well, it's a law. You always drop a bowling ball and you always see it fall, but that doesn't prove that it always will fall, because guess what? As soon as you go into orbit or whatever, it's not going to fall. So it's a law, not a theorem. A theorem is 100% always true no matter what, because it's defined by itself to be true. It doesn't sound like it makes a lot of sense to some people, especially people who kind of like physics, but they never really studied math proofs. They might be like, what? Laws are more secure than... No, theorems are the things that you can depend on. Laws are the things that you think are true. Theorems are the things that doesn't matter what you think. They have to be true no matter what. So you can look at the sun and you think, I think that's a burning ball of gas, but it could be a hologram. We could be tricked by someone. Okay. But Gödel's incompleteness theorem, that's a different story. Because no matter how complicated the statement is, if it's mathematical, you're not assuming anything. There's no hologram tricking you. Possible, because it's math. It's by itself. The only way it could be tricking you is if the reasoning itself has been infiltrated. And if it has, then there's nothing really you can do to reason in the first place anyway. The universe isn't even consistent enough. I mean, if I can't even take a notebook and write down math on it without the symbols changing, without my discretion, without my understanding, how am I supposed to even reason in the first place and talk about this type of stuff? So yeah, that's basically the difference between laws and theorems, I guess, or the difference between, observational science and mathematical, let's say, inferencing. So I could make a video on the Stack Overflow question sometime. I could make a video. I don't really, Into the Breach is an okay game. But it reminds me of too much of FTL in the sense that it is so difficult and frustrating to play. Actually, I get frustrated when I play that game and when I play FTL, because I feel like you make a little tiny mistake. The way the game works, to me, is like you make this little mistake and it just bites you. It just like destroys you. Like you make this dumb mistake, you move the guy to the wrong place at the wrong time, and then it just kind of sets this whole pile of, well, since you made that mistake, now this guy gets an advantage and this guy, boom. And you just like lose the whole game. It is kind of difficult. And that's like playing it on easy. I'm like, how is this game so hard? Man. I guess you just have to be really good or just sit there and think of it like chess. And I don't really like to play chess. So maybe it's more for chess players. I don't know. I'm the kind of guy who likes to code, or who used to like to code this little Java program to play chess for you. Or at least search, maybe one or two moves ahead. And not necessarily, a balanced 200 move ahead tree that, does statistical analysis or something like that. It has a whole bunch of pre-programmed, strategies. I just made those simple programs. You ever play the game 2048 on iPhone? Or the iPad, whatever. It's where you swipe up, down, left, and right, and you try to combine the squares that are powers of 2. So you have like 2 and 2. You swipe, and they slide together, and they make a 4. And then you try not to let the entire thing fill up with numbers, because if you do, then you lose. So you try to keep some open space. Now, if you get to the number 2048, then I guess you've won the game. So I was not good at that game at all. I could not figure out how. I was like, this is so hard. So I made a simulation in Java one time, and basically the way it worked was it simulated the game. It randomly would pick a spot to put in some twos or whatever. And then another part of the program would play the game. So what it would do is it would try to guess it would simulate out of all the possible places a new two could show up. It would add up it would make decisions on what it could do, and then it would give a probability of like that happening or something. Hold on, I'm trying to think. No, it would get an expected value, essentially. It would like add up how many points you'd get, like I think it would quantify how much open space there would be left. So it would be an expected value of how much open space. So if there was more open space, it would be more likely to go down that. It would want to go down that path more. So if it said swiping up is more likely in 5 moves from now to result in more white space than swiping down, then it would choose, swiping up as opposed to swiping down. And that's how it played. It just went off the expected value of white space. My initial algorithm was not the expected value. It was essentially the expected value just means average, by the way. The initial algorithm that I tried was the one that's trying to avoid death the most. So the one that minimized the worst case scenario. So the one that said okay, it's not likely, but it's possible that if you swipe up, you'll die. It would avoid swiping up then. But eventually it would corner itself. So even though it would try to avoid dying in the next 5 moves, maybe it would set itself up for failure in the next 6 or 7 moves, basically. So that algorithm, by being risk minimizer, being afraid, was worse than the expected value algorithm, which was, I'm just going to do whatever is most likely, whatever gives me the best total chance. The one that summed up all the total chances of all the possibilities, and it said, well, there's a chance that I'll die, or whatever. There's a chance that I could lose in 1 turn even, or something like that, or 5 turns, even if I do the best thing. But it's such a small chance compared to all this white space that I otherwise will get, that I'll take that shot, basically. So the expected value algorithm did pretty good, which makes sense because it's going off what is the sum of the most likely things to happen. So it's probably going to generally do pretty good at keeping the amount of white space up. So that's the game 2048. If you weren't able to keep track of what I was talking about. And I was just talking about how I made a simulation about it. So I don't know what else to talk about. I have a little bit of a beard that I need to shave off because I do not like facial hair. It drives me crazy. So I shave it off. But it's not like it looks that bad, even though it feels like it's, I don't know. It doesn't look that bad. Well, I don't know. Anyway, so that video that I posted about Tesla and Jesus and Ramanujan and Terry Davis and Dan Winter. Okay, so Terry Davis and Dan Winter, Terry Davis already died, but the thing is, he's the one who made his own operating system and his own version of the C programming language. Now, by making a just-in-time compiler, he was really, in my opinion, on the right track for how things like that should work. We should be reasoning about things at the high-level function. Now, do you need a compiler in the first place? I would say no. If we can if we can just do things with parse trees and not even use a just-in-time compiler, if we can use just interpreting at a higher, but it's a smart version of a smart way of interpreting languages, where you don't use files, because a just-in-time compiler, if you really think about it, it's taking it's taking something in something that you'd call a file structure, a file hierarchy, and it's basically treating a file hierarchy like it's a formal structure that makes sense, but it's really not. It's really not a well-defined thing. So a just-in-time compiler still is respecting files, and I would say do not respect files. They are not a beautiful thing. They are not a mathematically consistent idea. They should just not exist in your end product, in your end game. They just shouldn't exist. They don't make any sense. They don't have a well-defined structure. It's like what they're doing is they're taking a well-defined programming language and set of expressions, and then then saying, well, this is smart, but since we're dumb and we think we're smarter than whatever this programming language is, we're going to come up with our own way to organize it. And then people separate them into files and the file hierarchy, when the language itself is supposed to organize everything. So yeah, people thought Terry Davis was crazy. I don't know if it was because of his Christianity or because of his rambling on and just swearing all the time, but he was extremely brilliant. And just labeling him as crazy, I mean, sure, his brain, like something might have been going on with his health, and you can't just like blame him for that. Like if he's not able to concentrate for 20 seconds instead of 40, if he's concentrating for only 20 seconds instead of 40 seconds, okay, that's like his health. Okay, that's like some mental health, but that doesn't mean that he's crazy and he's coming up with incorrect propositions. It doesn't mean that his logic is like suddenly magically wrong. It doesn't mean that he's suddenly making these extremely weird behavioral decisions. Yeah, his behavior might change, but it's not like it's suddenly this weird, undefined, this guy's gonna go, kill 10,000 people, and there's absolutely zero justification. Like, even if he did, like, would there not be any justification for it? I mean, you already have, like, an extremely unjust society. So when somebody's, like, being called, quote-unquote, crazy, you can't treat them like they're not going to be a good influence on society. You have to treat them with respect and listen to them because they've learned something. They've already put their bodies through difficulty trying to improve this world, first of all. And then on top of that, there's already people treating them like crap and not believing them when they're trying to, when they're being rejected for being correct. So it's just, to me, it's kind of ridiculous. It's like, if you don't believe him when he's already coded it, like if you don't believe him and he has no code or anything like that to follow, that's one thing. But when he's sitting there and he's showing you how his operating system works, and you can see that it works, and then and that it has these properties to it, it's like you can't just be like, well, that guy's crazy. Oh, well, there's something wrong with him, and then ignore what he's doing. I mean, it just doesn't make any sense. I mean, did you say that the Google execs were crazy when they didn't believe in neural networks and artificial intelligence algorithms, but they believed in money because that's what everyone else believes in, and business rules and things like that? I was going around in the army telling people about neural networks back around like 2010 when people were like, what are you talking about? And guess what? Now they're a big thing. So you can't just like do that. That's not cool. That's not helpful. That's not going to get you really anywhere with the right people. If you just kind of click together and say, well, this person's crazy, and just because you can, it's not going to ultimately get you anywhere. So I respect him because he was just doing his best at what he could do, and he was good at it. He didn't let people just talk him down. I mean, there was a reason why he would talk down on how others did their work on MIT or whatever. There was a reason for that. It wasn't just this crazy rambling by someone. So, yeah, Terry Davis. Don't just think, oh, we need to do something about mental health. We need to listen to him and do what he said and respect him and regard him, because that's what we're supposed to do. Now, when it comes to someone who's still alive, like Dan Winter, people tend to be critical about his websites and how he has these kind of 90s style websites with tons of information in every corner, and then a lot of capitalization, and then a lot of association with any kind of alternative medicine you can think of. Auras, chakras, chiropractic stuff. Okay, so there's going to be tons of people out there who's going to be like, who's this guy? He's a scammer. Oh, who's this guy? He's crazy. Oh, there's something wrong with him mentally. Oh, what's going on? Okay, is he a true physicist or not? Because if he is, he's blown every other dang physicist out of the water. Because I've sat with quote-unquote real physicists at University of Illinois. I sat down and talked with one face-to-face. And you know what I get? I get this vibe of just like they know everything and you know nothing. That's the vibe. That's the thought that I detect from them. Oh, they know everything and you know absolutely nothing. Even if you want to talk with them about how it makes sense that a black hole, which is supposedly stretching space-time into one point, suddenly proves that we're in this holographic universe because, we can't store all the information, even because we have this law that says we have to store all the Planck lengths of information. But if the Planck lengths are being stretched, then the black hole takes up a certain amount of space. Well, is it being stretched or not? Right? Is it being stretched or not? Because if it's being stretched, then it basically can, right? And if it's not, then how do you know that the law holds near a black hole? It's just a law, like the bowling ball. You've only tested it. If you've only tested dropping a bowling ball on the surface of the Earth, you've only tested it in a very small fraction of the entire universe, correct? So why are you assuming that a law like that is more fundamental than the math itself, than the base reality of the universe? So that's what I would have talked with this physicist about, but I don't know. I don't remember if we ever talked, or if he just said, I don't have a lot of time though. Because I think they expect you to have, a quote unquote degree, or, have so many classes with equations that somehow say that you understand things. I don't know. Same thing with computer science professors. They don't seem to have time or want to talk with you. So that's why I'm going to, make my own tools and be like, hey, look, I don't need a compiler. Hi. I'm not crazy. I'm not Terry Davis. I'm not Dan Winter. But look, I also don't have my degree yet. But look, I can edit parse trees and run programs without compiling anything. Isn't that what Inspiration Basic does? I already have videos of it on YouTube. I can run programs, edit programs, without having to compile anything. So, I don't know why people don't think that's cool. I think it's the way we're going to do things in the future. But it's okay. I have to do Inspiration. And then I have to do something that works basically with I was like interested in C# and F#, and then I was like Lisp, and then I was like, what is going on here? I need like a good base language that kind of does everything. And that's how I got into the whole calculus of inductive constructions and things like that, which I eventually thought of after I started working at Runtime. And they were working on this C programming language, which I knew was Turing complete, but I didn't like C from the beginning, but it still was interesting what they were doing with it. So, math, programming languages. Think of them as the same thing, not separate things. Test-driven development, or functions that take code as input. They're the same thing. What's the difference? Tell me what the difference between a test case is and a function which takes code as an input. Guess what? Lisp does that. Lisp takes S expressions as input, right? And what does test-driven development methods do, or functions, or whatever you want to call them? They take code as input and give you a result, usually just true or false. Like, oh yes, this quote-unquote passes the test. Well, what if it's a GUI? How do you have to see if a HTML page is formatted correctly? Is that going to be a true or false, or is it going to be something that the user looks at and says, oh, I think that's good. I think so. So think about that for a second. Is it a function that takes code as input and returns a bool? So is code data, or are they two separate things? When you're doing your little lambda calculus practice, is your function and your your parameter, I should say argument. Is your function and your argument the same thing? Depends if you're doing the Y Combinator, right? So in the C programming language, every programming language, no matter what it is, it's always going to have those two levels. Okay, it's always going to have basically your function and your argument, right? Now the way, and it's going to be at different levels of abstraction. So in the C programming language, the way it works there is you have your variables, like your local variables, and then you have your pointers. And then you obviously have your heap space to make it Turing complete. Because if you don't have that, if you don't have what's called computational equivalency, then you'll be limited in what algorithms you can eventually make. But the thing is, in your structure, you have to be limited if you want to create a structure that's going to help you abstract on your programs. Okay, so that's what they try to do with Lisp. Lisp isn't just this open blanket heap. It's not just C, it's not just assembly code. Okay, it's a structured thing, but it's not typed well. Like, how do we type it more? Well, we make a typed version of it. Well, we have to do this and that and this and that. And eventually they come up with all this math, and it's called the lambda cube. And you have Haskell, which is made by Microsoft. Now that's good. Microsoft, those guys who made Haskell, even Microsoft probably doesn't even realize this. Most people working at Microsoft. But the team at Microsoft, those PhDs who made Haskell, they're smart. Because they made something. Now, I'm not going to say they know everything, but they made something that you can make a lot of security software and things like that with Haskell. It's still limited, and it still has the same problem that Lisp has. It still has the same problem because you're manually trying to match parentheses and things like that. They're not really thinking about the problem holistically. Now, Coq, C-O-Q, that was created by those guys in France, or I don't know if it was actually created in France, but I think it's from a French university or something. I don't remember. Just look it up. COQ. It's based on a mathematical logic system called calculus of inductive constructions, where you get the effect that you can't really get in any other system, any other programming language that I know of. You could probably make another type of system or another type of programming language that does stuff like this. But you have the effect of being much more versatile, much more powerful, and yet still what's called strongly normalizable, which means you still have expressions that provably reduce, which means this no matter what expression you come up with this in this grammar, it's not gonna be an infinite loop. It's not gonna keep growing on you. It's not gonna be. It doesn't matter. You don't have to prove whether this one reduces and this one doesn't. They always reduce. They always get smaller. If you process them, they eventually come down to one result. So that's what strongly normalizable means. Calculus of inductive constructions works that way, and it's purely functional. And on top of that, well, I should say with that, you have this interesting property where code and data can coexist and be treated as the same thing in such a way where you don't have to explicitly kind of keep them in two separate groups. They can kind of switch places without you worrying about things getting out of hand. You don't have to worry about, and when you don't have to worry about stuff, that means you can automate, because you can make some computer program that just generates them, searches through them. Because now you don't have expressions being generated that just, some of them grow bigger and some of them reduce. Now 100% of them reduce. So now you can automate things. So I'm going to keep going back to this. Calculus of inductive constructions. It solves pretty much all the problems of programming languages. All the current problems. Now, Gödel, if anyone says you can 100% solve all the problems for all eternity, Gödel kind of disproved that with his incompleteness theorem. Calculus of inductive constructions is technically everything you can come up with, as long as it's finitely lengthed in its description, is going to be limited eventually in some way. But what's beautiful about this one is it takes the recursion, it takes the idea of the induction going on to the next level, because it allows you to apply the math to itself in a new way that other programming languages don't really do. Lisp kind of tries to do it, but in a way it doesn't really work out. In this case, it works out because now it iterates. If you look up calculus of inductive constructions, it has this little n for natural numbers, and it iterates. It starts at 0, or maybe it starts at 1. I don't really remember. But it counts up 2, 3, 4, 5, 6. And your expressions, as long as one with a higher number is dealing with one with a lower number, then it's okay. Then it's allowed, but not the other way around. So as long as one of them is bigger than the other, going the correct way, what that does is they're both versatile. They're both expressions that can be defined in whatever ways you need. And the only thing that you need to check is that little number. And that's why it's strongly normalizable. That's why it works. Look it up. If you don't believe me, look it up. This is programming language research. This is called, I think you call it pure type systems, or pure type theory, or the system of, I'm not sure what you call it exactly, but it's basically pure type systems. And I think it's more powerful than what people realize. I think what happens in society is, in technological research, is that over the years, we keep balancing between these two ideas. And this is why I think they say, there's people online who say that there's no way that we can have a quote unquote silver bullet, which suddenly increases how well we code things or whatever by tenfold. I think this is the reason, okay? It's because we have this really strong kind of equilibrium. Everyone's trying to improve what we're doing at the same time. And you have people switch sometimes between taking the logic systems that are out there, like the programming languages that are already out there, and just like improving like the analysis, like the statistical analysis of it, making something more complex with it so that it functions better, it works better, it's more automated, it does whatever task it's supposed to be doing better, you know. And then we have like these really cool things like artificial intelligence with all its statistical usefulness, neural networks, genetic algorithms, all this automation and things going on. And then you have, on the other side, you have this mathematics and this grammar logic upgrade system where people are like, wait a minute, we're doing all this stuff in this system that's like, it should be outdated because this is better. And they say, well, we shouldn't use, I don't know, the math people might say, you shouldn't use propositional calculus, you should use this other thing, whatever. And they upgrade the base math that we're using. They basically upgrade the kernel or the axioms or whatever you want to call it. They want to upgrade that. They want to change it, because what they're saying is the base model which we're doing everything with is no longer good enough. It's no longer efficient. And the other people are like, what are you doing? What are you doing? Why fix it? It's not broken. Because they're focused on what they're building. And they've already constructed all this stuff, and they think, oh yeah, we'll just stick with that. Because why would you want to rewrite the whole, operating system? Why would you want to use a whole different... And they don't understand that the improvement process is this balance. It's this equilibrium. The more you build on a foundation, the better it's going to be for the kind of the short-termish, but the harder it's going to be to switch over to another foundation, potentially. The harder it's going to be to realize, oh, there's an even bigger foundation. And if you didn't study Gödel's incompleteness theorem, you won't understand that we need to. There's always going to be these times where we have to switch the foundation to a new foundation. You're never going to be stuck with the same foundation. And he proved that. It's like this is like at the heart of mathematics. This isn't something you can like avoid. You can't just pretend it doesn't exist. Oh, well, we'll just keep doing things this way. We'll keep using C. he proved that there's no consistent and complete logic system. And so we have to listen to that. We have to understand that and work with that, because that's just how it works. That's just the way it is. Yeah. I like rambling, guys, in a way. I don't like it too much, but I kind of like it a little bit. And I ramble a lot, but I don't always record it, and I think I should. So, the way I think of it right now is, it sucks that Terry Davis died. This is the way I think of like things in technology right now. Technology, the way I value things is, I don't care about, whether someone has a PhD or, whether they're super famous or rich, like Elon Musk, or even if they're alive or dead. I just look at them and I'm like, whether people believed them or not, was what they were doing correct or not? Okay, when it comes to Terry Davis, okay, people didn't really give him too much of a chance, it seemed like, and he was smart. Okay, so when it comes to the computer world, operating systems, things like that, Terry Davis he could have made some more cool stuff. Like, I just think that it sucks that he died. When it comes to computer science, though, I think there's people out there who literally believe the universe is just this binary set of Planck lengths, and so it's like this really intense, like really high amount of information, but it's still a computable system. It's still like based on a finite amount of information. So even though there's a lot of information, it's still finitely lengthed, and so we're still basically limited. But then there's also a different way of thinking, which might be the truth, and that is that the base system for our universe is not a computer. It's not Planck lengths, but it's actually it's more of like the model that you see in like calculus, where you have like the real number line, and you can keep zooming in forever. And it's basically waves. Everything's waves. Even the things that we think are like Planck lengths or finitely lengthed proofs, or whatever you want to call it, bits, discrete math. Even the things that look like it's discrete math are not actually discrete math. They're just probably a 1 or probably a 0, but there's still this tiny chance, and we're just allowing we're just seeing, how should I put this? We're seeing these waves, these things that are actually waves in like a real, like, you ever seen the sinusoidal mappings in like a calculus class or something like that, where you can keep zooming in, or like a fractal. No matter how much you zoom in, even if it's 10 bazillion trillion whatever, you can keep zooming in forever, and it's always deeper. Okay, that's completely separate. That's a completely different idea than bit wise, like Planck lengths, which once you zoom in far enough, you only get a couple ones and zeros here and ones and zeros there, and that's it. Those are two completely different models. They're very, very different. They have totally different implications. So if we have one model, it means a totally different type of universe than the other model. They're totally, completely different. That's the point that's what I'm trying to say. And when you have this universe where everything is waves, okay, you can still see things that look like it's discrete systems, but what it really is these waves that are interacting in such a way that they've just I don't know what the word for it is. They've essentially created or came together and just kind of, you know, when you look at when you look at water and you just see waves, and you make like a whole bunch of waves by throwing in some rocks, and the waves come and hit each other. If any two waves that hit each other at the same time, they come up a little further. They add together twice as much. So these waves in the wave universe, if you believe that the universe is made up of waves instead of discrete Planck length bit math, you'll still see those bits, because those are just the waves kind of adding together at these higher and lower points. Okay, the reason why I'm saying all this is because that is, I think, the type of universe you have to think of. That's the type of universe that you have to reason about if you're going to understand the stuff that Dan Winter talks about. Because he is, if you know, from my perspective of mathematics, sometimes I branch out and kind of talk about either physics or computer science. Okay, so if Terry Davis is kind of like the computer science guy, right? Dan Winter, from my perspective as someone who appreciates mathematics, he's more of the physics guy. And to think of his models, he talks about things like the phi ratio, things like that. He doesn't talk about computability. He doesn't talk about things like Gödel's incompleteness theorem. He talks about things like phi and about things that apply to waves, in like calculus and things like that. And his in one of the things that he talks about that I don't think many people understand, but what I think makes a lot of sense, is what I would call, he doesn't call it this, but I would call it a singularity. Now, I don't remember him actually using the term singularity. I don't know why. But when you're doing math, a singularity, I don't know if you guys, if everyone watching this knows this, but a singularity is basically where your model breaks down. Okay? So when you're talking about something that's quote unquote infinite. Now, if you watch Dan Winter's videos, he talks about infinite. He calls it infinite. He literally uses, the Greek letter phi, because he's actually talking about the golden ratio. But he's not crazy when he says that. You might think, oh, well, he's just being like, he's just trying to get your money or something. He's working with all these chiropractors, all this alternative medicine, or whatever. He's just trying to, what is he talking about? And he doesn't sound like a mathematician. He doesn't sound like a physicist. Well, if you actually study math, if you actually do math and you actually study it the right way, and you actually do it, one of the things you learn is that singularities are not like this well-defined thing. It's this thing that happens when your model breaks down. One example is the function. What function was it? There's a function where it's undefined at like 0 and 1 or something. And it's because it asymptotes. Oh, we'll just talk about tangent, okay? When tangent asymptotes, what is its value? Well, your teacher, is going to tell you, oh, it's undefined. They're not going to tell you it's infinite, because infinite is not, because they're looking for a real number. Infinite is not a real number on the real number line. Okay? So people, it's very common for people to misunderstand what infinity means. Okay, a child thinks of it as, oh, this really, really, really big thing that just it's bigger than everything. Okay, but when you talk with mathematicians who do formal proofs, they talk about infinite as, basically they think of numbers as having two different properties. One of them is a magnitude. Okay, it has to be represented by some finite number. And another one is like a comparison state. It's like, okay, is it greater than or less than this other number? And then when they call it cardinality. And when they talk about infinite numbers, they just say, oh, well, pick any number and or any natural number or any real number, and they'll just say it has greater cardinality, but it has no magnitude assigned to it. So it has no real number or natural number assigned to what's called its magnitude, but it always has what's called greater cardinality. So that's why everyone just kind of thinks of it as bigger. It's super big. Or when they say that God is infinite, they think, oh, that means he's bigger than everything. That means, he's bigger. Okay, they don't think that it could mean that he's tinier or that he's different or he's, you know what I mean? They don't think of it as anything else. They just think of it as bigger. And that's not really what math tells us. That's not really what is going on if you follow the math precisely. That's not really what the math says. And that's why, for example, like when it comes to Ramanujan sums, when you add, let's say 1 plus 2 plus 3 plus dot, 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 okay, people will say, well, obviously it has to be infinite, or it has to be, it can't be this negative 1/12 that they're talking about. Well, who's to say? Because it doesn't, the point is, if you take calculus 2, you'll know that the series doesn't converge. Now, if it converges, that's one thing. But if it diverges, what is a divergent series? It's just a divergent series. It doesn't, the math doesn't say anything else about it. So you can assign properties to it. You can assign numbers to it and say, well, this number is associated with that. So what Ramanujan did is he assigned negative 1/12 as the property. Now he uses the equal sign. Okay, I don't care if you use the equal sign or whatever. You just have to define what you're doing. Okay, but in his sum, he adds the natural numbers 1, 2, 3, 4, 5, and gets negative 1/12. Okay. Whether you want to call that summation, whether you want to call that whatever you want to call it, you can just call it, probably should just call it a Ramanujan sum. But it's an infinite sum. It's not a finite sum. It's not something you can do with a computer. It's not something that you can say, oh, well, I got in an argument with this guy about Minecraft, for example. I was trying to explain to him that it was not actually Turing complete because you could not actually build a machine that would grow its own memory to contain whatever algorithm you give it. So if something's Turing complete, I should be able to make an algorithm which keeps printing out, for example, all the Collatz integers in order or something like that. And before these command blocks existed in Minecraft, I don't think it was possible to do that because you'd have to physically go out and build a redstone computer bigger and bigger and bigger and bigger manually. Whereas in a simulation like Conway's Game of Life, you could build a machine once, a finitely lengthed machine, and it would expand itself out, and then it could print you all the Collatz integers or give you a representation of it with bits or whatever. So there was a clear difference there. This one had unbounded memory, whereas Minecraft did not. And he said, well, I could go out and just, pretend I put infinite redstone first, and I said, well, then you're changing the world generation algorithm. Because the way it works, the whole point of computer science, we were in a computer science building when I got in an argument with him about this. And I was trying to explain, one of the core concepts about computer science is you're always working with a finitely lengthed or a finite amount of information. That's like the core point. Okay. When you're talking about the Turing machine, all right, you start off with a finitely lengthed program, and then your memory for the Turing machine is what's called unbounded. Okay, unbounded means it means the total amount of memory that you have available to use is infinite. But the amount of memory that you are using at any point in time is still going to be finite. We just don't have a maximum for what that is. But it will never be infinite. Okay? So you'll never have a Turing machine running a simulation, and at some point in time you say, that's interesting. The Turing machine just used its infinite amount of memory at this point in time. No, it never does that. It always has it always uses one slot of memory, maybe two. Okay, now it's using 3. Maybe it's using 10 quadrillion, but it never uses infinite memory. It just never does. Even if it keeps growing forever and ever, it always is finite. That's the whole point. That is like one of the base ideas for most of the theorems, most of the mathematics in computer science. So why did I branch off and talk about all the infinite versus finite? Okay, so we're getting back to Dan Winter. So, and the Ramanujan sums. So Ramanujan talked about the sum of the natural numbers being negative 1/12. Okay. So he had a different set of axioms. So if you go by Occam's razor, his axioms actually made sense. Because he actually used less axioms. If you look at the definition, if you ever take your calculus class, Calc 1, 2, and 3, really all it's doing is it's just saying, well, for an n-dimensional object, this is the relationship between its n-dimensional volume and its n-1 dimensional surface. That's all calculus class is really saying. Now, when I say calculus, I'm not talking about lambda calculus. That's a different, the word calculus is different than the academic set of classes, calculus 1, 2, and 3. Those are two different terms. So in calculus 1, 2, and 3, that's all you're learning. You're just learning the relationship between an n-dimensional volume of an object compared to its n-1 dimensional surface. That's really everything. If you take all your Calc 1, 2, and 3 classes and look at everything you're doing, it's all that same thing. And the theorems themselves, I'm bringing myself back to the point where I'm talking about the Ramanujan sums and why they're better, I would say, than Calc 1, 2, and 3s. And the point is, their theorems that define convergence and divergence and everything like that, they're kind of just sloppy. They're not holistic. They're not beautiful. They're not mathematically, I would say, intrinsic to the universe. Okay, they're not necessarily anything special. Okay, it's just like this very mechanical statement that says this is convergence and this is divergence. Why? Because we said so, and we feel like it, and we feel like you can't add positive numbers to get a negative number because infinity doesn't wrap itself around. And I've literally had people tell me like, oh, infinity doesn't wrap itself around. You're going against absolute logic. Hold on. I'm going against absolute logic when I have a formally well-defined, explicit definition of a Ramanujan sum, which has simpler axioms, according to Occam's razor, So none of this is human bias. None of this is my opinion, right? This is just a pure mathematical formulation. So I'm the one who's going against pure logic here. I'm the one going against absolute logic. Nope. Because there's nothing in absolute logic that says anything about infinite sums having to add up to a positive number. There's nothing. There's plenty that says, oh, if you have finite numbers, if you have a finite 5 and a finite 4, and you add them together, you're going to get a finite 9. And if you have a finite x and a finite y, you're going to add them together. And if they're both positive, then you're going to get a finite z, which is also positive. Sure, that's absolutely true. But notice how I said finite. They're all finite. They're not infinite. No one ever proved anything about infinite numbers being added up and having to be positive. Nobody ever proved anything about that. Show me there's no axioms about that. Absolutely none. And it's not going against absolute logic. It's not going against absolute proofs or anything. Ramanujan sums, they make sense. They're fine. They actually allow you to assign a value to an infinite sum that doesn't converge. That's what they are. They're really awesome. They're really cool things. They make sense. And people don't like it when when they think they have math all understood and they have this foundation and they're like, yes, this is math and nobody's gonna hurt it. They you come by and you go dink and the whole thing just cracks under them and they fall into the water. And you're just like, you thought you understood math, but nope. And you use formal math to prove them wrong, or to show them that your foundation makes complete sense. It's hilarious. So there's people who think that they're secure in what they know, but in reality they don't actually understand math the way they think they do. So that's going back to Ramanujan. Now, why did I bring up Ramanujan and Ramanujan sums and this whole convergence thing? Well, it has to do with the waves. Remember I was talking about, I'm coming back, I'm bringing this all back together, okay? Terry Davis, when I talk about him, I'm talking about computer science stuff, okay? I'm talking about type theory, things like that. Stuff that I personally was interested in, stuff that I personally studied. When I talk about Dan Winter, I'm talking about waves. I'm talking about stuff that you can reason about with finitely lengthed proofs, but the universe itself is like this wave. In his model, in his understanding, I think the universe is made up of waves and everything. That, like a model that they try to reason about in Calc 1, 2, and 3, basically. His model for a universe is waves. And it's not discrete Planck lengths. It's not discrete bits. It's waves. Okay, and that's important because with waves you can get singularities. You can basically have fractals. You can have things that literally infinitely zoom. Okay, this isn't something you get in a Planck length universe. Okay, this is something that you get in a wave universe. This is a totally different game. Okay, totally different ball game here. Okay, because it's I think Mandelbrot set, but real life. Like this actually physically exists in this scale. Okay, Mandelbrot actual set really existing in reality at that scale. Okay, just think about how crazy that is. Okay, think about what that means. That's not billiard balls. That's not. You can't just do some math and say, well, I'm going to hit this ball over here and it's going to bounce this way and it's going precisely X, meters per second, things like that. Okay, it's not Newtonian physics. It's not Galilean physics. Okay, it's not even going to be fully represented by Einstein's general relativity. Okay, you're not going to understand it all just with a couple of. I don't know too much about quantum physics, but I don't think it's going to be represented, very completely by, a little set of quantum physics equations that are just modeling what people are observing and testing. Okay, this is a fractal universe. Okay, this is like a universe where things, if waves can actually propagate themselves from being tiny to being big, if there's an actual mechanic for that changes like everything. That means scale is like another dimension. Now, I've seen this video or this documentary that basically said it's like another half a dimension or something. It's like 3.5 dimensions or whatever. Or fractals are another dimension, basically. Okay, this is another dimension. This is like a scale dimension. It's not it's not like an orthogonal. When you think dimension in math, usually you think of time as being like this thing that you can plot on a graph, and then you have like maybe height here or whatever, and then you have width and you have depth. Okay, you got like these 4 dimensions that you usually think of more like a linear fashion. But when you're talking about scale, and it's actually infinite scale, okay, you have to account for everything in your model, no matter how deep it goes. So it could be super, super, super huge, and there could be bigger and bigger things, and then there could be tinier and tinier and tinier things. So like the real number line, you ever hear your math teacher ever say there's more numbers between 0 and 1 on the real number line than there are natural numbers. So if you count for all the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, you can make a mapping from all those to the real number line, but you can't make a mapping from all the numbers just from between 0 and 1, just that little segment. You can make a mapping from the natural numbers 0, 1, 2, 3, 4, 5 all the way to infinity. You can assign each one of those to one little point on the real number line between 0 and 1, but you can't assign all the numbers between 0 and 1 back, because it's even more dense in that little segment, because you can keep zooming in. Okay, so this is powerful. This isn't just like, oh, we're gonna model the natural numbers between 0 and 1. This is even denser than that. This is more information than that. Okay, this is like you keep zooming in, and there's more. So in that sense, you have essentially another dimension. And it's like this dimension of depth. But you can't really assign, you can't treat it like it's a typical dimension. Okay, where you can just locate something. So if you have 3-dimensional space, you can locate something by giving 3-dimensional coordinates. Okay, with this, it's different, because it's almost like you need an infinite amount of coordinates just to find something, because you have to say, well, it's in the first half. Well, where is it in that half? Well, it's in this second half of the first half. And that's only the rational numbers. Excuse me. Then again, I guess the rational numbers, I think, are countable, so you only need 1 coordinate technically for those. But for the reals, even if you tried to split it in half, you still wouldn't find something. Isn't that crazy? Even if you tried to split it in halves, you couldn't find something. So you'd have to assign an infinite amount of coordinates. Just to find something. So and there's a lot of theorems on this. A lot of mathematicians actually, I forgot the name of the theorem that most mathematicians who would, worked on this, the one theorem, they would commit suicide. It was really weird. But there's like a theorem that says like the cardinality of the reals and the cardinality of the naturals are they right next to each other, or is there some kind of set that's between them such that it's got less cardinality than the reals but more cardinality than the naturals? I forgot what it's called, but it's like this really famous theorem that a lot of mathematicians in history tried to prove, and a lot of them went insane and like committed suicide. But that's not the point, because I'm not talking about math as much right now as I'm talking about physics. Okay. And you only need to understand the math enough to know first of all, what math really is. And second of all, what the difference between the two models of the universe I was talking about are, so that you don't get trapped into thinking one or the other, or trapped into thinking you understand what one is incorrectly. Okay. But Dan Winter, okay, in his model, in his understanding of the model of the universe, as it's a fractal, okay, you have waves, okay, and then you have this what's called a singularity, which, like I said in math, singularity just means your model breaks down. Okay, it doesn't mean, we can't assume we know what infinite means. I already went into all this with Ramanujan sums and all this. Okay, so in Dan Winter's model, you have waves. Okay, that create a singularity. And he doesn't use the term singularity, but he's basically talking about a singularity. Okay, he talks about going, through the speed of light or something like that. And what he's saying, it might make sense from like a certain perspective. It might make perfect sense to him. But to someone who doesn't understand the base models that he's thinking of, to someone who just thinks of things in terms of some other sense, like maybe someone thinks of things in terms of Newtonian physics or something. Okay, so a lot of people don't even understand the speed of light. A lot of people just think, oh, the speed of light is just this magical thing where things suddenly just can't go faster. Okay, a lot of people don't understand this stuff. A lot of people. Okay, but what he's really saying is he's saying there's a specific way to get a singularity where the model breaks down. Okay, this is the mathematical way to say it. Not as an expert, I'm just saying these are the math terms involved here. Okay, you have a singularity, and when you have a phi ratio, you have what he says, you're adding and multiplying waves. So I think what he's saying is there's this sweet spot. There's this function, or this wave with a specific function with a specific parameter, right? Such that it creates the singularity that you want. Okay, it's kind of like the ultimate of all possible known holy grails. It's like this ultimate thing of the most ultimate possible thing. Okay, this is like he's saying this is like everything that you've ever heard of in all spirituality, anything about God, anything about mysticism, whatever. It's all explained by singularities, because basically what he's saying is we're in this wave universe where we have these three-dimensional objects and things like this, and they're all constructed by these waves, and we just see like these objects, and we can think about them and reason about them and do all these things. We can have fun. We can take a basketball and throw it into a hoop and have fun, and we can hear sounds, and we can see light, and all these things happen in our universe. Okay, he acknowledges that, but he's saying then there's something totally different. There's something totally separate from all of that. Totally different. Okay? There's something completely like set apart. And remember, in the Bible, it's in spirituality, there's actually a term called holy. And literally what it means is set apart. It means different. It means like of a completely different category. Okay? So Dan Winter is saying, okay, this is totally different. This isn't a sound wave that just starts here and ends over here. This is a fractal wave. This is a wave that basically goes from a 0 point, a literal 0 point, like something that gets infinitesimally small. So it literally like goes down to infinity. And going the other direction, it gets infinitely large. So it's like a type of wave that's a fractal wave. And by having and then your locality rules, so like the speed of light and all that, that's all based off the space-time continuum. So whenever someone talks about going faster than the speed of light, okay, you can't do that relative to the space-time continuum around you. So if you can stretch space-time in such a way that you go through a wormhole or something, okay, you've quote-unquote went faster than the speed of light, but just from a different perspective. You didn't go faster than the speed of light relative to the space-time continuum that you were actually physically touching, like you were physically in. Okay, if you took a path of whatever, let's say it was a spaceship, okay, and you plotted it, the space-time continuum around the spaceship or whatever it is, that's not going to, it doesn't break the speed of light through that path. But from a different perspective, from someone from a different point of view, they see point A and point B from a distance, and they didn't go inside the wormhole. They just see point A and point B. They say, oh, well, you just went backwards in time, or you just teleported, or you just went faster than the speed of light. They see something weird because they're looking at it from the perspective of someone who didn't go through the same path as you. And the space-time continuum was not the same for them as it was for you. So what he's saying, what he's basically getting at is this. He's trying to explain a singularity that lets you break the rules that we all can know of already. Like we know the rules of the speed of light and all that stuff. We know the rules of gravity. We know the rules of all these things that have to do with regular with typical, how should I say this? The typical parameters, I guess, the typical context. So whenever you're going slower than the speed of light, whenever you're talking about energy that's not extremely off the scale of anything we've ever measured, whenever you're talking about, just billiard balls bouncing off each other and things like that. Regular sound waves, regular light waves that we typically measure. Okay, those are the rules that we understand. We have all these experiments and tests, and we have this set of rules that we're like, okay, this is the universe that we know. It's not necessarily the entire universe or the set of all possible rules. It's just the ones that we measure, the ones that we know. Okay. But we don't really know what happens in a singularity, obviously. We know from math that a singularity means that your model breaks down. So we know that these rules that we understand, we know that all the set of these rules that we came up with that in the space that we understand, we know that that somehow will break down when there's a singularity. We don't know what will happen. We don't know, maybe it's Hawking radiation when it comes to, black holes or something. We don't always really know what it is that happens, but we just know that it breaks down and something special happens, something different happens. So when we do something special, like accelerate particles, to the speed of light and collide them to each other, we know that something special will happen. We don't know precisely what it is, per se, but we just know that something different will happen because it's a singularity. Okay. So Dan Winter, what I'm trying to say here to the average person who doesn't necessarily understand a lot of physics or a lot of math, or maybe understands one or the other, but not necessarily, both, or I don't know. But what I'm trying to say is what Dan Winter is trying to show us is a way to create a certain type of singularity and what really happens at that singularity. That's what he's doing. That's what he's talking about. Okay, so he's not this crazy guy. He's not just like he lost his mind or something. He actually understands something. And it's going to sound crazy. It always sounds crazy when somebody talks about a different model for the universe. It always sounds so ridiculous. Okay? And his goes so far, so deep that, it's going to talk about, he's going to talk about spiritual things. He's talking about your soul. He's talking about, time travel and all this stuff. And it's going to sound crazy, but that's because it's dealing with something that we don't experience on a day-to-day basis. It's something that we're not used to. It's something that we haven't modeled. So, of course, if you look at math and how it works, of course, something different is going to happen when you have a singularity. And if you figured out a way to have a singularity with like a phi ratio wave that's fractal, then of course something is going to happen. Of course something very fundamental about the universe is going to be realized, and we're going to be like, oh my goodness, I did not realize the universe actually worked like that. That is crazy. Of course we're going to label it as crazy. And we're going to think, what is this? Is he trying to just get our money? I don't know, maybe he's trying to get someone's money or something, for all I know. They have these iOS apps where they're, measuring your heart. But mathematically, there's nothing like wrong. There's nothing suspicious from a mathematical point of view. There's nothing suspicious about what he's talking about what he's doing. In fact, it's math that helps me believe him, whereas a physicist might not believe him. Because a physicist will just say, well, you're just talking about a whole bunch of stuff that I don't know about. But as a mathematician, I would say, you're talking about stuff that I don't know about. Therefore, it's probably correct, because I know that there's a singularity in there. So, don't just throw out Dan Winter thinking, oh, he can't be right. Oh, this guy's crazy. Oh, he's just... Don't throw him out thinking that. Because no matter what it is, no matter what the explanations for the entire unified theory of the universe is, it's going to be something that pretty much everyone is going to think is crazy. It's just, that's just how it is. So, I like Dan Winter, okay? I think people who study stuff like that and who know their field that much in depth, they are special people. They are pretty awesome people. So, regardless of what anyone else says or thinks, I think, I'll just say I regard him. Okay. So, just stick to the truth. Stick to the truth and don't judge someone because you feel like something's not true. Okay? Because in math, there's not a lot that says you can prove that something is impossible with physics. In fact, there's not really any mathematical statements that says this is impossible with physics. There aren't. And that's the truth. People think that it is. People think that, we're going to be rational. But if you actually look at the facts, if you actually look at the math, there's nothing that says you can say that something in physics is impossible. There actually isn't. There's nothing that says when you let go of a bowling ball that the bowling ball can't just float there. And guess what? Once you go out into orbit, guess what happens? It does just float there. You can say something mathematically is wrong. You can say that 2 + 3 is not 7. But that's self-defined. All of the axioms are contained inside of its own statement. So people who think that they know math, but don't actually know math, and people who think that they understand physics, but don't actually understand physics, will probably label Dan Winter as like crazy or something. But in reality, he could be the most legitimate person we know for actually sticking to the truth the entire time and going down the rabbit hole. So, I will see you guys later. I hope you like my video. And if you think I'm a little bit crazy, I appreciate you as well. I'll see you guys later. Bye.